When we study aircraft generators, we learn that most of the electricity used by an aircraft is produced by the generator. But when an aircraft's engine is not operating, the generator cannot produce current. To provide power for starting, when an external source of power is not available, a storage battery is provided in all Army aircraft. Two types are commonly used: nickel-cadmium batteries and lead-acid batteries. Before we learn how batteries provide electricity, we will first review so that we are sure we know what electricity is. The wires, cables, and buses in an aircraft electrical system are conductors of electricity. These conductors are composed of atoms which are shown here in magnified form. Each atom has a nucleus or core which has a positive electrical charge. Surrounding the cores are orbiting electrons. The electrons revolve around the core at extremely fast speed. In this sketch, the electrons are not moving so that we are able to see them. Each electron in an atom has a negative electrical charge. Some materials have atoms which are quite stable, but in materials which are good electrical conductors, the atoms are unstable. Electrons are constantly transferring from the outer orbit of one atom to the outer orbit of another. It is this instability of electrons which makes a flow of electricity possible. Wires and other conductors are made of materials with unstable atoms. When no current is flowing in a wire, electrons are constantly transferring from one atom to another in random directions. There is no pattern to the movement. Electrons may move up, down, right, left, backward, or forward. But when an electrical current flows through the wire, two things change. The number of electron transfers is greatly increased, and all of the transfers are in one direction, the direction of current flow. Thus we learn that electrical current is a directional flow of electrons. What causes the electrons to flow? The answer is pressure. The application of pressure to electrons in a wire is similar to the application of pressure to water in a pipe. The water is caused to flow because there is more pressure at one end of the pipe than at the other. A pump makes water flow through the pipe by causing increased pressure at one end of the pipe. In a similar way, a generator makes electrical current flow by causing increased electron pressure at one end of the circuit. A generator is called an electromagnetic device because it uses magnetism to produce electrical current. In this film, we are going to study an electrochemical means of producing electrical current. An aircraft battery is called an electrochemical device because it utilizes a chemical reaction to cause electron flow. We will deal with two different types of batteries: lead-acid batteries and nickel-cadmium batteries. For many years, the lead-acid battery was the only type used in aircraft. It is the same type battery used in automobiles and trucks. The lead-acid battery, however, is being replaced by the nickel-cadmium battery, which, as we will learn, has many advantages. All types of batteries work on the same basic principle. The principle can be demonstrated with two metal plates. The plates must be of different metals or metallic compounds. Using an extremely sensitive meter, we find that when the dissimilar metals are connected to each other, there is a momentary, very weak flow of electrons from one plate to the other. The reason for this electron flow is that one of the two different plates has more electron instability than the other. Here is what happens. If this plate has the greater number of unstable electrons, some of its electrons will rush over to the other plate when they are connected. A sufficient number will move to the other plate to create a balance of electrons on the two dissimilar plates. In its simplest form, this is how a battery uses a chemical reaction to create an electrical current. One battery plate has an excess of electrons. The other has fewer. When they are brought into contact, the pressure of electrons in one plate causes a flow of electrons to the other plate. The plate from which the electrons move is called the negative plate. The plate toward which they move is called the positive plate. The customary symbols, a minus sign for negative and a plus sign for positive, are used on batteries. The electrical current produced in this demonstration was very tiny and very brief. To increase the current flow and to keep it flowing for a long period, it is necessary to make the electrons constantly flow from the negative to the positive terminal. To do this, the plates are placed in a hard rubber or plastic container. The container is then filled with a liquid so that the plates are completely surrounded and saturated. The liquid is called an electrolyte. In an aircraft battery, the electrolyte is a chemical solution. The chemicals used in lead acid and nickel cadmium are not the same, but in both types, the electrolyte provides an electrical path between the positive and negative plates. Thus, when a load is connected to the battery terminals, a complete circuit exists in the battery via the electrolyte. This makes a continual flow of current possible and greatly increases the electron pressure from the negative terminal toward the positive terminal. From this point on in our description of battery function, we will deal with lead acid and nickel cadmium batteries separately. In a lead acid battery, the negative plates are made of sponge lead. This is pure lead of a very spongy or porous consistency. The positive plates are made of lead peroxide. The electrolyte is a mixture of sulfuric acid and water. With this combination of chemicals, the current provided by electron flow is quite strong when the circuit is closed. The electrochemical reaction, which causes electrons to flow from the negative to the positive terminals, also causes the sulfuric acid and water electrolyte to become weaker. As the battery discharges, the acid content decreases and the water content increases. At the same time, the negative and positive plates are affected. The pure lead content of the negative plate and the lead peroxide content of the positive plate are greatly decreased. They are replaced by a coating of lead sulfate. In battery shop terminology, the plates are said to be sulfated. As the electrolyte becomes weaker and the sulfating increases, the battery gradually loses its charge and finally is fully discharged. The chemical reaction is spent and the electron flow ceases. Current can again be drawn from the battery only by charging it. Charging is accomplished by connecting the poles of the battery to a generator or battery charger. In the aircraft, while in flight, the aircraft's generator keeps the battery at full charge. During servicing, an auxiliary power unit or a battery charger may have to be used to recharge a battery. The negative terminal of the charging unit is connected to the negative pole of the battery. The positive terminal is connected to the positive pole. Current is forced through the battery in the opposite direction. This charging current at slightly higher voltage than the battery's rating reverses the chemical reaction. The lead sulfate coating on the plates is changed back into pure lead and peroxide. At the same time, the acid is restored to its original strength. Charging is complete when the sulfuric acid strength is at maximum. The strength of the sulfuric acid electrolyte provides an accurate means of determining the state of charge of a lead acid battery. The strength or specific gravity of the electrolyte can be measured with a device called a hydrometer. With a hydrometer, you can accurately determine whether or not a lead acid battery is adequately charged. A hydrometer consists of a glass tube with a rubber bulb at one end and a piece of flexible tubing at the other end. Inside the glass tube is a float. The float is completely sealed, and it contains a paper strip with a graduated scale printed on it. One end of the tube is weighted so that when the float is placed in a liquid, it will float with the weighted end down. To use a hydrometer, the bulb is squeezed and electrolyte is drawn through the flexible tubing into the glass tube so that the float is immersed in the electrolyte. The hydrometer is held with the tube vertical, and the depth to which the weighted float sinks in the electrolyte is read on the graduated scale. When a battery is fully charged, the acid content of its electrolyte is high. The float will not sink deeply into the liquid. A fully charged battery has a reading on the graduated scale between 1275 and 1300. As the battery is discharged, the acid in the electrolyte is depleted. When the battery is in a medium state of charge, the float will sink deeper into the electrolyte so that the reading will be between 1240 and 1275. Any battery showing a reading of 1240 or lower should be recharged or replaced with a fully charged battery. When the float sinks deeper to a reading between 1200 and 1240, the battery is in a low state of charge and lacks sufficient capacity for satisfactory operation. Since temperature affects the reading shown on a hydrometer, some hydrometers contain a thermometer to indicate the temperature of the electrolyte. A direct reading correction scale is included so that the proper factor can easily be added or subtracted from the float reading. With minimum experience, you can use a hydrometer to accurately determine the condition of any lead-acid battery. In construction, a lead-acid battery is simple, compact, and rugged. In our sketches, we have seen only one negative and one positive plate. To provide adequate power, many individual plates are required. The 5 sponge lead negative plates and the 4 lead peroxide positive plates are connected by lead connectors into units called plate groups. Each connector has a terminal post to serve as negative and positive connections. The negative and positive plate groups are arranged on the connectors so that the two groups will slide or sandwich together. Thus, the negative and positive plates are close to each other to provide maximum electrochemical reaction. The negative group always has one more plate than the positive group. This improves the electrochemical action and the voltage output. To keep the negative and positive plates from contacting and shorting out, separators are inserted between each of the plates. The separators are made of a very porous material so that the electrolyte can circulate through them. With all the separators inserted, the unit is referred to as a cell group and is housed in a container. This one is cut away so that the ribs in the bottom can be seen. When the cell group is inserted, we see that the ribs come in contact with feet on the bottom of the plates. This provides a space at the bottom of the container where material shed from the plates can accumulate as the cell slowly deteriorates. Without this space, the material would pile up at the bottom of the plates and cause a short. Most aircraft batteries have a separator protector which is fitted across the top of the cell group to hold the separators firmly in place and protect them from vibration or servicing damage. The cell container is closed with a cell cover, which is sealed to the container with an acid-resistant compound. Holes in the cover permit the negative and positive terminal posts to extend out of the cell. At the center of the cover is a hole for the vent cap. The vent cap screws into threads in the cell cover. This cap is different from the caps found on an automobile battery. On the outside, the cap seems quite similar. However, when it is cut in two, we find that it is hollow and contains a lead weight. At each end of the cap, there is a vent hole. When the battery is in normal position, the vent holes are open, permitting gas formed in the battery to escape. However, when the battery is turned on its side or is inverted, as it might be in an aircraft, the valve closes the inner hole and seals the cell. Electrolyte, which might leak through the vent, is kept inside the cell. Thus, this specially designed cap prevents electrolyte from escaping, but permits gas to escape. A single fully charged cell has a rated output of 2 volts under normal load. Army aircraft requires 24 volts. Therefore, aircraft lead-acid batteries are made up of 12 2-volt cells. The cells are series connected by cell connectors which are welded to the terminal posts. To provide ruggedness and electrical shielding, the cells are permanently molded into a metal case which is painted with acid-resistant paint. A gasketed cover clamps to the case, providing an airtight seal. To permit gas and spilled electrolyte to escape, 2 vent tube openings are provided. Many batteries have a quick disconnect battery terminal assembly, which simplifies installation and removal of the battery. The assembly completely covers the terminals, thus preventing accidental shorting. Note that the irregular shape of the mating parts prevents reversing the connections. Nickel-cadmium batteries offer important advantages. They can stand idle for long periods without damage and without losing their charge, and they are not damaged by freezing as lead-acid batteries are. The chemical materials used are, of course, different in a nickel-cadmium battery. When the battery is fully discharged, the negative plate consists of cadmium oxide, and the positive plate is nickel oxide. The electrolyte is not an acid, but a strong alkali called potassium hydroxide. These are the components of the battery when manufactured and before initial charging. When a charging current is applied to the battery, the negative plate loses oxygen and is chemically transformed into metallic cadmium. At the same time, the positive plate gains oxygen and is converted to a highly oxidized form of nickel. The practical result of this chemical conversion is that the negative plate now has an abundance of electrons which provide electron pressure when a load is attached to the terminals. As discharging proceeds, the chemical action is reversed. The negative plate is changed back to cadmium oxide. And the positive plate once again becomes nickel oxide. Compared with a lead-acid battery, a nickel-cadmium battery will deliver a very steady voltage output even when discharged at a high rate. Two other advantages of nickel-cadmium batteries are that they can be recharged in a very short time by the constant voltage method, and they are not permanently damaged by overcharging. Another important difference between nickel-cadmium and lead-acid batteries is that the electrolyte potassium hydroxide does not change during charging or discharging. For this reason, don't forget, a hydrometer cannot be used to determine the condition of a nickel-cadmium battery. The cells in nickel-cadmium batteries are thinner and lighter in weight than lead-acid battery cells. The negative plate group and positive plate group are sandwiched together as in a lead-acid battery. The plate separators consist of nylon fabric and cellophane. The cell case is of molded nylon, and since shedding from the plates is no problem, space is not required at the bottom to collect debris. Cell connectors replace the terminal posts of lead-acid batteries. Since the connectors are threaded, the individual cells can easily be disconnected and removed from a battery. On nickel-cadmium batteries, vent plugs are used rather than non-spill caps. These plugs are set to relieve gas pressure in the cell if the pressure exceeds 5 pounds. They also prevent electrolyte from spilling. Since the vent plugs are firmly torqued, a special nylon plug wrench is required to remove and replace the plugs. Each cell of a nickel-cadmium battery has a nominal rating of 1.3 volts, so that 19 cells are required for a 24-volt battery. The cells are housed in a steel or fiberglass battery case. A suitable cover is provided to close the case. Electrical connection to this battery is made through a standard quick disconnect fitting, which also has an irregular shape. Since both nickel-cadmium and lead-acid batteries are used in Army aviation, a dangerous hazard exists if proper precautions are not observed. The two electrolytes, sulfuric acid for lead-acid batteries and potassium hydroxide for nickel-cadmium batteries, must never be allowed to contact each other. Watch what happens when this does occur. Never use tools or implements for one type of battery on the other. Never work on the two types in the same area. Never replace one type with another without thorough cleaning first. This means cleaning all the components. Aircraft are almost as dependent on a properly functioning battery as they are on fuel, especially when operating away from an established airfield. Power must be there, ready to crank the engine. Flight is impossible with an engine that can't be started. Don't let a defective battery stop your aircraft.